In this video, I will derive Maxwell's relations. First, du equals dq plus dw. This dq and dw are inexact differentials because q and w are path functions. However, because internal energy U is a state function, we can imagine a reversible process in which U is changed by du, and thus du equals dq reversible plus dw reversible, and dq reversible equals TdS by definition. The definition of ds is dq reversible over t, and dw equals negative p external dv. In a reversible process, p external equals p. Therefore, the equation becomes du equals TdS minus pdv. This equation holds for a reversible process and also for a irreversible process because this internal energy is a state function. This entropy, volume, TMP are all state functions. By definition, we have H equals U plus PV, A equals U minus TS, G equals H minus TS, and then we can derive the differential forms of H, A, and G correspondingly. dH equals TdS plus VdP, dA equals negative SDT minus PdV, dG equals negative SDT plus VdP. We will use du, dH, dA, and dG to derive the four Maxwell relations. First, du equals negative PdV plus TdS, and then look at this equation. We know du over ds equals T if V is constant, and it's here. Du over ds equals T if volume is constant. And also du over dV equals negative P if ds is 0. Du over dV at constant entropy is negative P. So we got this two first derivatives of the internal energy, and we learned in calculus if U is a state function, well it is, and then the order of taking the first derivative does not matter. We can do delta U over delta S first, followed by V, or we can do delta U over delta V first, followed by S. And if you look at the top, this part here, delta U over delta S at constant volume, it's simply temperature. So we're gonna plug in temperature here, and we're gonna plug in negative P here as well. So we got the first Maxwell relation. Delta T over delta V at a constant entropy equals delta P over delta S at a constant volume with a negative sign in front. Given dH equals TdS plus VdP, we can see dH over ds equals temperature if dP is 0. So that's here. Or dH over dP equals volume if entropy is constant. So that's here. And then we use the calculus rule. Because H is a state function, the order of taking the first derivatives with respect to S and P or P and S does not matter. And again, we plug in this part is temperature, that's from here. This part is volume, that's from here. And then we have the second Maxwell relation. The third and the fourth Maxwell relations are more useful. You'll see over here, it helps us to compute the entropy change when volume changes. It also helps us to compute the entropy change when pressure changes. So we're going to look at this. Given this dA, A is the Helmholtz free energy, equals negative S dt minus PdV. We know dA over dt equals negative S if volume is constant. That's here. And then dA over dV is simply negative P, so it's here if temperature is constant. And again, calculus rule, A is a state function, so we can do this. We can change the order of taking the first derivatives. And then we plug in this negative S here, and we plug in negative P here, and we have the third Maxwell relation. Again, this is useful because now we know how entropy depends on volume, as long as we know how pressure depends on temperature at a constant volume. And this part is very easy to evaluate. Given dG equals negative S dt plus VdP, we know dG over dt is negative S. and dg over dp is positive volume. And also pay attention to the condition. Constant pressure here, constant temperature here. G is a state function, so we can again use this calculus rule and plug in dg over dt at constant pressure is negative s, and dg over dp at a constant temperature is a volume. So we have our fourth Maxwell relations. And we're going to summarize the four Maxwell's relations here. 1, 2, 3, 4. Again, the last two are more useful. This one is delta S over delta V, how entropy depends on volume at constant temperature. This is equal to delta P over delta T at constant volume. We can derive this easily. Beta is how the relative volume change depends on temperature. Kappa is how the relative volume change depends on pressure. So beta is 1 over V times delta V over delta T at constant temperature, and kappa is negative 1 over V times delta V over delta P at constant temperature. So for an ideal gas, delta P over delta T is simply P over T or nR over V, and then we can compute this entropy change to be nR times ln V final over V initial for an ideal gas. For solids and liquids, you simply look up the values of beta and kappa. The last one tells you how entropy depends on pressure if temperature is constant. And this is delta V over delta T at a constant pressure. And again, beta is simply 1 over V times delta V over delta T at a constant pressure. So this is just definition of beta. And again, it's very easy to look up the value of beta for liquids and solids. For an ideal gas, beta is actually very simple. Beta is equal to just 1 over T. So this guy, delta S over delta P, is V over T, and V over T is just nR over P. So the change of entropy is negative nR times the logarithm of P final divided by P initial.